Good afternoon, class. This is lesson 11, covering section 3.1. We're going to be talking about the determinant in greater detail. I mean, we've seen briefly the determinant, how to take the determinant for a 2 by 2 matrix. We had that formula with AD minus BC, right? We're multiplying one diagonal, subtracting what we multiplied the off diagonal. But we haven't really, beyond like the inverse formula, we haven't really talked about what is so significant about the determinant. We know it has some relationship with inverses. We know it has a relationship with the invertible matrix theorem. We need the determinant to be non-zero in order for a matrix to be invertible. But we haven't really dealt with any determinants for a non-2 by 2, right? We've done determinants for 2 by 2s. We haven't talked about how do you handle a determinant for anything that's not a 2 by 2. That's what we want to focus on in chapter 3. And as we continue in chapter 3, we're going to talk about lots of different determinant properties, what's special about the determinant, why we care about it, how it's going to help us do other things in linear algebra. So that's what we're looking at for today. Homework 3 should be posted today. There's not as many sections we're covering for homework 3. It's only going to be covering 3.1, 3.2, and 3.3, I believe. Let me double check the schedule real quick. So there's only 3 sections that'll be covered in homework 3. Now I want to make sure y'all have ample time for that. So I'm probably, originally in the schedule, it says that was going to be due the 25th. But I want to make sure that y'all do have enough time for that. So I'm probably going to push that to the 26th. That way you'll have that extra day instead of making it due Tuesday. So it'll be due July 26th. I'll put that on Canvas. And again, that's going to be covering sections 3.1, 3.2, and 3.3. So all of chapter 3 is going to be in homework 3. All right. There's also, now I realize there was no lecture video for Friday. So in light of that, and this video being posted later in the day on Sunday, there will not be a participation question that goes along with this lecture, this section. So there's no participation questions due today. I realize it's Sunday. I want you to enjoy the weekend. This is a Monday through Friday kind of deal. I don't want you to have to be really busting yourself trying to get through this class on the weekend. So with that being said, there isn't anything due today. I'm just posting this video today so that you can go ahead and see this and watch this. This is going to be starting us off for chapter 3. And then tomorrow we'll pick up where we left off with the schedule and begin section 3.2. All right, so 3.1, we are discussing the determinant. So let's get on in that. So some reminders. We know from the invertible matrix theorem that a matrix is only invertible. So let me write it out here. Invertible matrix theorem. A is invertible if and only if the determinant of A is not 0. And so far, kind of the only explanation we've had so far is we know for a 2 by 2 matrix, A, B, C, D, the inverse is this formula where we divide by the determinant, AD minus BC, and then we flip the diagonal, and then we change the sign of the off diagonal. So this is our formula for a 2 by 2, and we said, what is the determinant? Well, the determinant is this calculation, AD minus BC. But why is that the determinant? Where does this come from? We know that this happens to work for our formula for an inverse of a 2 by 2. We checked that in chapter 2 last week. But in more general terms, what is happening here? Why does this work? Well, from the invertible matrix theorem, we also know that A is invertible if and only if and only if A is linearly independent, right? We need a pivot in every column. Okay, well, let's think about that for a moment. What happens then in this case when we're trying to reduce this matrix? Well, if I were trying to reduce this matrix, I would want to get a pivot for A, right? Which means I need to get zeros below it. Okay, well, how do I make that happen? Well, kind of, first of all, an easy way to see this is, let me first, because right now there's no A in the second row, right? So what am I supposed to multiply A by so that I can subtract things? Or what do I multiply row 1 by so I can get a 0 down here? So first of all, I'm going to modify row 2 by multiplying it by A. And this will result in A, B, A, C, A, D. Okay? Now, how does this help? Well, to row reduce this, now it's a little bit easier to see. If I take row 2, and I'm going to take row 2 and subtract C times row 1. All right, well, why does that work? Well, if I multiply row 1 by C, I'm going to have AC. And if I subtract, that'll cancel out this AC down here, right? So first, I multiplied row 2 by A so that I could see there's an A here. And then that tells me, OK, what can I multiply row 1 by to get rid of this C, or now to get rid of the AC? OK, so what happens here? Well, when we do this, we're going to have A, B. It'll be AC minus AC. That'll give us 0. And then we'll have AD minus CB, or I'll rewrite it as BC. Now, what just happened here? AD minus BC, we know that's the determinant. But we also know from the invertible matrix theorem, a matrix is invertible if and only if the matrix is linearly independent. Well, when I row reduce the matrix, it can only be linearly independent if this calculation, AD minus BC, is not 0. So this is, in fact, where the determinant comes from. The determinant is the result of row reducing your matrix, and it's whatever occurs in the last entry of your matrix. But if it's a square matrix and you need to be invertible, then that means you need to be linearly independent. That means you need a pivot in every column, so you can't have any free variables. So that means in this very last entry, it must be not 0 in order to be linearly independent. This is where this determinant requirement comes from, and this is where this formula is going to come from. All right, well, that's our determinant for a 2 by 2. How do we find the determinant for a 3 by 3? All right, well, as you might imagine, a 3 by 3 is a bigger matrix. If you're trying to reduce a 3 by 3 matrix, it does get kind of messy, but we're going to carefully work through this. All right. I also want to go ahead and introduce some new notation here that we haven't used so far. Now, part of this notation we have seen, we know for a matrix, I can rewrite it in this notation where each entry has 2 indices, like ij, indicating which row, which column I'm talking about. The first entry is referring to the row. The second entry is referring to the column, right? So I can write out a 3 by 3 matrix in this fashion. And in part, I'm using this notation here because this is easier than if I wrote out A, B, C, D, E, F, G, H, I, right? I'd have a bunch of different letters running around. So instead of having so many different letters, I'm just going to use this row column notation that we've already seen. So this part is not new. However, what is going to be new here is that I want to introduce this idea of a submatrix. So what is a submatrix? A, I, J. So note I'm using capital A because a submatrix is still a matrix. A sub ij is the submatrix submatrix of A where row I and column J are removed, right? So for example, the submatrix A11 is the matrix where I'm going to cover up row 1, column 1, right? So I'm covering up row 1, column 1. What am I left with? I'm left with this little 2 by 2 matrix. A22, A23, A32, A33, right? So this notation is going to be very important for what we're about to do next. So I want you to have this in the back of your mind. All right. Next, we know in order to find the determinant, we're talking about, we need to row reduce this matrix, right? We need to get it into echelon form. All right. Now, for the sake of space and time, I'm not going to go through all the steps of row reducing this matrix just because it's the exact same methodology we did for the 2 by 2, right? You're going to multiply, if you want to get zeros below A11, then you're going to multiply row 2 by A11, so you get that A11 to appear in the second row, and then you'll multiply by things, subtract, so on and so forth, just like we did for the 2 by 2. So if you want to do that extra practice, you can. But I'm just going to go ahead and jump to what is the reduced form here. Also, we're assuming that A11 is not 0, right? If it turned out that A11 was 0, well, then you could just swap the rows, right? Swap it with one of the rows where there's not a 0. But if the entire column was all zeros, then we would know there's a free variable, in which case it's not linearly independent, so the determinant is 0. So there's nothing to calculate then if you see a column of all zeros, right? A column of all zeros means you have a free variable. So assuming this is not kind of that trivial case where the determinant is non-zero, then that means there's some kind of non-zero entry in this first column. Let's just suppose that this first entry is not 0. Okay, so what happens? Well, when you reduce this matrix, we end up getting a funny pattern happening. We're going to have 0, A11, A21, or sorry, 22, minus A12, A21, and then this third entry of the second row we're going to have, and I'm kind of running out of space here, but this isn't super important yet. Because remember, the determinant is the last entry of the matrix. That's what we're really concerned with. I'm just writing in these details so you can see. We have A11, A23, minus A13, A21. All right. And then we're going to have 0, 0, because these are supposed to be pivots, right? And then this last entry, we're going to have A11. Now, because this formula is so long, I'm going to write this as a Greek letter delta, this triangle symbol. And we're going to talk about what this delta is if you go through all the row reduction here. Part of the point we're getting at is the determinant is whatever this delta is, right? Because I could just take this third row, divide the whole thing by A11, and I'm left with delta. So the determinant of the matrix is the result of row reducing the matrix, figuring out this last entry, right? Now, of course, we would like a formula for that instead of having to just row reduce the whole thing. So what's happening here? Well, this formula, and I'm going to try to write this out. Remember this submatrix idea? We're going to need this in just a moment. All right. So I'm going to write out the formula you get if you carefully do this row reduction. You're going to find that the determinant equals A11 A22, A33, minus A11, A23, A32, plus A12, A23, A31, minus A12, A21, A33, plus A13, A21, A32, minus A13, A22, A31. All right. Now, this is the determinant for every single 3 by 3 matrix. Do I suggest memorizing this long, messy thing? No, do not memorize this. This is just what that formula is when we row reduce the matrix. However, there are some patterns with this formula that we can rewrite this and simplify it into a nicer picture. All right, so how are we going to do that? Well, first of all, notice this pattern of like this alternating plus minus thing that's going on, right? Maybe there's something we can do with that. Well, in fact, we look at this first piece, I have an A11 in common. A11, if I factor out the A11, then I have A22, A33 minus A23, A32. Plus, and I have an A12 in common here, A23, A31 minus A21, A33. And then I have an A13 in common for the third term. Okay, so what's happening here? What's this pattern? Well, I have A11 times something. That's the first term of the first row. And then I have A12 something. That's the second entry of the first row. In other words, I'm taking the first row of the matrix. I'm taking each piece. Oh, hold on. Sorry. For this step here, I actually, and this will be more apparent in just a moment, I actually want to subtract or factor out a negative A12. This is an important step we're going to see here in just a moment. I want to factor out a negative here in the middle. So I could rewrite what's in the parentheses here as A21, A33 minus A23, A31, right? Okay, now, back to trying to recognize the patterns here. I also, because I factored out a negative in the middle in order to get this to clean up nicely, this is going to be more apparent in just a moment. Make sure I wrote this correctly. Yeah, okay. So we're taking the first row across the matrix, and I'm taking each entry of the first row and I'm multiplying it by something. What am I multiplying it by? What is A22 times A33 minus A23 times A32? Well, if you imagine covering up this first row, first column, that piece in the parentheses is the determinant of this submatrix, right? A22 times A33 minus A32 times A23. In other words, what's happening here? I'm going across the first row, I'm picking each entry, and then I'm multiplying it by the submatrix where I remove that same corresponding row and column. Well, the same thing happens here. If I have minus A12, well, A21 times A33 minus A23 times A31, that's the submatrix which results, the determinant of the submatrix that results from crossing out the first row, second column. This is the determinant of the submatrix A12. Well, so on and so forth. Now we have this very nice cleaned up formula for finding the determinant. And so what are we actually doing? Well, if we're trying to find the determinant of a larger matrix, we can break it down into actually trying to find the determinant of its submatrices. Right? So in fact, this formula is actually what's going to work nicely for us here. Okay? But I also want to highlight, notice this alternating plus minus pattern that had to occur in order to get this determinant of A12 to appear in the middle. Right? So I needed this alternating plus minus pattern for this determinant here, because that's how things are going to work out in your row reduction of your matrix. Okay, so this is actually the formula we want here. And we can look at some examples. So let's do an example that uses this formula. Let's see how it works in practice. I'm going to leave the formula at the bottom. All right. And we're going to have this example. Let's say A equals this matrix 1, 5, 0, 2, 4, -1, 0, -2, 0. All right. According to this formula, to find the determinant of this matrix A, I need to go across this top row. I'm going to take each entry and multiply it with the determinant of its corresponding submatrix. So I'm going to take A11, which is 1. I'm going to multiply it with the determinant of the submatrix where row 1, column 1 is marked out. I'm going to do -5 times the determinant where its corresponding row and column is marked out. That's going to be A12. And I'm going to add 0 times the determinant of the submatrix A13. Now here's something nice happens. If you do have some zeros in your matrix, well, then that means the corresponding submatrix that goes with that entry is going to be multiplied by 0. So we have this long formula, but if one of the entries ends up being 0, it makes the calculation easier for us. All right. So what's our determinant then? Oops. Well, we're going to have 1 times the determinant of A. The determinant of A11. I'm covering up row 1, column 1, which leaves me with this 2 by 2 submatrix, 4, -1, -2, 0. All right. -5 times the determinant of its submatrix. I'm covering up row 1, column 2. So what am I left with? I'm left with a 2 by 2, which is 2, -1, 0, 0. All right, so what's the point of this? Well, when we have some bigger matrix, I can use this formula to rewrite it as a determinant of smaller submatrices, right? But then once you break this down enough, eventually you get down to the determinant of 2 by 2s, which we already have a formula for the determinant of a 2 by 2. You multiply the diagonal and then subtract what you get when you multiply the off diagonal. So what's our final answer here? We're going to have 4 times 0 is 0, minus -2 times -1. Well, it's really the same thing as just 2 times 1. Minus 5 times 2 times 0 minus 0 times negative 1. So we're going to have 0 minus 2 is negative 2 minus 5 times, well, this is 0 minus 0. So we're left with a final answer of negative 2, which means I've not done anything with this matrix. I didn't row reduce it. I didn't do anything else. All I did was calculate its determinant using this formula. Well, its determinant is non-zero. What does that mean? Well, that means everything else in the invertible matrix theorem is true about this matrix. It's invertible. It's linearly independent. There's a pivot in every column if you row reduce this. But if there's a pivot in every column, and this is a square matrix, that means you have a pivot in every row. Well, that means if you have a transformation which is using this as its standard matrix, that transformation is one-to-one. It's onto. All these other properties automatically are true for free just by this one little calculation, right? So this can give us a quick and easy way of calculating the determinant. You're going to go across the top row, take each entry, and multiply it by its determinant of the submatrix. But you want to note this alternating plus minus pattern. In fact, in general, what's happening here, well, it's kind of like a checkerboard. You start with plus in the top left corner, first row, first column, and then you're just going to alternate signs. So this means for any size matrix, and you can double check this for a 4x4 if you want. For any size matrix, you're going to have this checkerboard pattern of plus minus. Right? So this is going to occur. Now, another thing to note here is that we know for row reduction, you could, if you want, swap two rows, and it's the same matrix, right? Remember, each row just represents some kind of equation. At least if it's an augmented matrix, each row corresponds with an equation. So swapping rows doesn't change the matrix, doesn't change the meaning of the matrix. Well, why am I bringing this up? Well, imagine if instead of working with row 1, you instead chose to use row 3. Why would we care about row 3? Well, look, there's extra zeros here that row 1 doesn't have. So what am I getting at? While we have this formula that uses row 1, you can just as easily calculate the determinant by using whatever row you want. The trickiness, though, is that you also need to remember this plus minus pattern, right? That's going to tell you what sign it should be. So this calculation, I used row 1, right? This used row 1 as its calculation. Well, what if instead I use row 3 to find the determinant of the matrix? My blue marker is dying. This is brand new, too. That's disappointing. Okay. Well, plus minus pattern. So plus minus plus. That means row 3 is also going to start with a positive. So I'm going to have the determinant of A is positive 0 times the determinant of A 3, 1, right? So now I'm marking off, I'm looking for the submatrix where that entry's corresponding row and column are marked out, right? Okay. Minus, because I have to alternate signs, a negative 2. So this is a good point I want to highlight here. If you have already a negative in the matrix, well, when you alternate signs using that determinant formula, you might run into double negatives. So you want to watch out for that. That can change your answer. And if you were to leave off this negative, it's going to throw off your answer and give you a wrong answer. So be careful here. Times the determinant of A 3, 2. Again, we're going across the third row. So I'm marking out the chorus. I'm finding the submatrix where row 3, column 2 is marked out. Plus 0 times the determinant of A33. Okay. Now, why is picking row 3 instead of row 2 nice? I have these two zeros, right? Which means when this simplifies, I only have one determinant to calculate. Now, I'm also going to introduce this new notation. You'll see this sometimes pop up in the textbook. When you're trying to take the determinant of a matrix, instead of writing determinant of a matrix like I did up here, sometimes for shorthand, just to make the notation quicker and faster, we write these absolute value bars instead of using the bracket bars. And so when you see these absolute value bars around a matrix, that means you're taking the determinant. So I'm looking at the submatrix A32. So I'm covering up row 3, column 2. What am I left with? I have the submatrix 1, 0, 2, -1. Right, so I have these absolute value bars instead of bracket bars. And this just means I'm taking the determinant of this 2 by 2. All right, well, that's 2 times 1 times -1 is -1, minus 0 times 2 is 0. And lo and behold, -1 times 2 is -2. I got the same answer with a lot less calculation, right? So sometimes picking a different row to find your determinant can be faster or quicker or easier. Now, the last kind of pattern I really want to highlight here is that this is also going to work by cleverly picking a column that works nice, right? So here we've picked row 1, row 3. What if instead I want to pick a column, right? So we're still going to use that same formula, except now we're saying you don't have to just pick row 1. You can pick whatever row you want. In fact, you can also pick whatever column you want. So let's suppose I choose column 3. I pick column 3. Okay. Well, again, remember the plus minus pattern, the checkerboard pattern, plus, minus, plus. So I have a positive 0. The determinant of A equals 0 times the determinant of its submatrix. I'm not really going to even worry about trying to figure out what that is exactly because it's going to be multiplied by 0, so who cares? So 1, 3. Now I have plus, minus. I have a double negative, right? I have minus -1. So I'm just going to go ahead and write it as positive 1 times the determinant of its corresponding submatrix, A, 2, 3. Again, I'm just covering up its corresponding row and column, right? So as you get more practice with this, you're going to start doing this very quickly, where you just pick whatever row or column you want, and then you're going to multiply it by the corresponding submatrix where you mark out the row and column that entry comes from. So when we get to this next step, there's also like another plus 0, but that's just going to be multiplied by 0, so who cares? I'm not going to write it. All right. So what's our answer then? Well, we get 1 times the determinant of A23. That's going to be 1, 5, 0, -2. So we get -2 minus 0, in other words, -2. Again, we got the same answer. So you can pick whatever row or column you like. Sometimes if there's a row with more zeros, that's an easier one to pick. Or if there's a column with more zeros, that's an easier one to pick. So go ahead and do that, and that's going to lead you to your answer. In fact, it's going to lead you to an easier calculation, an easier answer, a faster answer, right? So we've done this with 3 by 3s, but for that matter, I can do the exact same thing with a 4 by 4. So let's see how it works out when the matrix gets even bigger. So let's suppose instead our matrix is 1, 2, 3, 0, 4, 5, 6, 7. And then I'm going to do 0, 0, 8, 0. And then 9, 10, 11, 0. All right. Now I've intentionally made up this example so that if you want to calculate its determinant, well, there might be a row or column that's easier to work with. For example, I could pick row 3 because I have a bunch of zeros there, right? I could also pick column 4. That has a bunch of zeros there. Either way, that's going to work. But you also still want to be careful of the alternating plus minus pattern, that checkerboard pattern with the plus minus, right? So still keep that in mind. I'm going to pick row 3. You can also pick row 4. You're going to get the same answer either way. It doesn't matter which one you pick. I'm going to pick row 3. So the determinant of this matrix A is what? Well, plus minus plus. It's going to be 0 times a submatrix, or times the determinant of a submatrix. What is that? Well, I'll be multiplying it by 0, so who cares? I'm not going to write it down. Plus 0, all right? Minus 0 times the determinant of a submatrix, but again, to be multiplied by 0, so who cares? I'm not going to write it down. Plus 8. Plus 8. Now I can write out times the determinant of a submatrix. What submatrix? Well, it's the submatrix where the row and column, which contains 8, which contains this entry, right? I'm covering up row 3, column 3. What am I left with? I have 1, 2, 0, 4, 5, 7, 9, 10, 0, right? And then I would have another minus 0 over there, but again, who cares, right? Okay, well, now what happens? Well, now we found for this 4x4 matrix, its determinant is the same thing as 8 times this submatrix. In fact, we're trying to take the determinant of this submatrix. Well, this submatrix is a 3x3, which means I've got to use that formula again to break this down until I'm taking the determinant of 2x2s. But that's okay. What's the determinant of a 3x3? Well, pick your favorite row, pick your favorite column, do the exact same process. Well, in fact, what's handy about this submatrix is that column 3 has 2 zeros. So let's pick column 3. Pick column 3. All right. So now the determinant of this matrix, we still have this 8 on the outside. I'm going to put this whole mess in parentheses. You know, actually, I'm going to put it in brackets just so that we don't get confused. So I have 8 times. Now I want to take the determinant of this submatrix. I'm picking column 3. Well, I have 0 times the determinant of submatrix, so who cares? Minus 7. Remember that plus minus pattern, right? So this is minus 7 times the submatrix. I'm going to cover up its corresponding row and column. So I have 1, 2, 9, 10, and no other pieces. So now what happens? Well, if I multiply the 8, I have a negative 56 times the determinant of this 2x2, which we know we have a formula for that. Multiply the diagonal. 10 minus 9 times 2 is 18. Now, admittedly, I picked some numbers here that the determinant kind of comes out a little bit nasty to calculate here in the end. But that's okay. It's still not too bad. We're just using the same determinant formula. 10 minus 8, 18 is negative 8. Negative 56 times a negative 8 will be positive. So we have, right, 10 minus 18 is negative 8. 56 times 8. So if I've done all these calculations correct, we get a final answer of 448, which means this matrix, I didn't have to reduce it at all. I don't have to reduce this matrix at all. Just by using this determinant formula, I could find its determinant, and its determinant is non-zero. So what else is true about this matrix? Everything in the invertible matrix theorem. If you row reduce this matrix, you're going to have a pivot in every column. It's linearly independent. It's invertible. The columns are linearly independent. You have 4 pivots, which means if you have a transformation that uses this matrix as its standard matrix, it's 1-to-1. It's onto. All of those other things, the invertible matrix theorem, are automatically true for this 4x4, just by this one little calculation, right? So this is kind of where the power of the determinant really starts to kick in, that just by doing this one calculation, we can find out a lot of information about a matrix without ever actually having to modify the matrix, without ever actually having to reduce the matrix, right? This is going to give us some power here to allow us to figure out some things with less work, with a very quick calculation, right? So you can do this for a 5x5, a 6x6, a 7x7. It doesn't matter how big the matrix is. You're going to use this exact same formula. Pick your favorite row or column. Remember the checkerboard plus minus pattern. Take each entry of your favorite row or column and multiply it by the determinant of its corresponding submatrix, right? What's the corresponding submatrix? It's the submatrix where you mark out the row and column that the entry comes from. All right. And then rinse and repeat. You do the same thing. If you have a 7x7, you do it once. Now you have a 6x6. Do it again. Now you have a 5x5. Do it again. Now you have a 4x4, right? You continue using the formula over and over and over again until it breaks down to a 2x2. And then you can use the formula we had for a 2x2 by multiplying the diagonals. All right. Now, of course, this current methodology is only really going to be, it's only going to work out nicely if I happen to give you a matrix which has nice numbers. If I give you a matrix which doesn't have zeros, well, then what do? I mean, then you're going to have a lot more submatrices to deal with, right? So in practice, depending on your matrix, sometimes this calculation can get very messy, right? How do we handle those occasions when the matrix might be messier and you don't have a bunch of zeros, like in this example I've cooked up? What do you do when you don't have a bunch of zeros? Well, that's going to be what we're going to talk about more as we continue in Chapter 3. But for today, for 3.1, I really just want to drive home this basic idea for the determinant, how we can use this formula, and then we're going to look at how to handle more difficult cases, more difficult examples, more difficult scenarios later in Chapter 3. So in 3.2, 3.3, we're going to talk about more methodologies in terms of how do you handle it when the matrix gets worse. Okay, well, that's going to be all for today. Again, there's no participation question. So take this video as just the opportunity to cover the material for 3.1 so that you know it. And then you'll be prepared for tomorrow's material when we begin section 3.2. All right, so that's all for today. If you have questions, by all means, let me know. Reach out to me. We'll talk about it. Office hours are still on Tuesdays and Thursdays. Otherwise, best of luck. I'll see you tomorrow.